Hello everyone, this is part 2 of lesson number 12 over waves. In this part, we'll talk about the nature of light, or what we call it the dual nature of light, as a wave and as a particle. In order to understand this dual nature of light, we need to go over the story of understanding light, the historic background behind the theory of light that started thousands of years ago. The first question we ought to answer is, how do we see what we see? When we look at a pencil, yellow pencil, how do we see it yellow? So we knew early on that it has to do with eyes. The Greeks proposed that the source of seeing comes from our eyes, that basically our eyes produce some type of probes that enable us to see things. Al-Hazen proposed that our eyes do not send light or do not send probes. They basically collect light from outside source, and that explains why we cannot see in a dark room. In his book Kitab al-Manadir, which is the book of optics, he basically invented what we call right now the scientific method. He used experimentation and observation to arrive to his theory about light. He described his experimentation in details, providing the ability to anyone to replicate them. He used mirrors, lenses to experiment and substantiate his findings. He used his knowledge of light to deduce that the Earth's atmosphere is finite in thickness. He was able to calculate the thickness of the atmosphere by calculating how long the twilight lasts. He correctly concluded that the light remains in our atmosphere even after sunset is because light bends whenever it enters our atmosphere, and hence he was able to predict the phenomena of refraction, or what we call it the atmosphere refraction index, and hence twilight even after the sun sets. His estimation to the thickness of our atmosphere is around 40 kilometers, which is actually 1/2 of our current calculation to the atmosphere thickness. In addition to the property of refraction, he also understood the concept of camera obscura. A camera obscura is basically a small opening on one side of a dark box, allows the light to go through it from the outside, projecting images inside the box on the other side of the wall. The image, however, is inverted and upside down. Ibn al-Haytham was able to explain how camera obscura works and how light travels in a straight line, as evident by the light from top high projected on the lower part of the image, while the light from the bottom is projected on the top part of the image, and hence he was able to explain the reverted image. He was also able to explain the structure of the eye and why the moon looks larger, which is basically an illusion. All these findings were published in his book, the Book of Optics, which, in addition that it was the foundation of current optics, it is the first or the early evidence of controlled experimentation that was ever recorded. So thanks to Ibn al-Haytham, we know now that we see things because there are sources of light, like the sun, like light bulbs, and the light that is emitted from the sources of light hit objects, and whenever it hits objects, it's reflected of those objects to our eyes, and hence we can see them. Of course, the light that comes from the sun passes through vacuum, unlike sound that cannot go through vacuum. Light will pass through vacuum, and we know now that it's made of electromagnetic waves. And the reason we see the pencil yellow is because most of the spectrum of the colors were absorbed by the pencil, and mostly the yellow was the wavelength that was reflected. But the question remains, is light a particle or wave? Is it movement of particles or is it wave propagating? Isaac Newton proposed that it was particles, he called them corpuscles, and he was able to use the refraction property to support his hypothesis. Refraction is basically the bend of the light whenever it moves from one medium to another medium that has different density. For example, when light goes from a medium that has low density, like air, to a medium that has higher density, like water, it will bend because it slows down. You can think about it in terms of you are pushing a cart or a dolly on a smooth surface and you suddenly move from the smooth ceramic flooring to a gravel road. What will happen to the speed and the direction of the dolly? You will notice that the speed will decrease when you move from a smooth surface to a rough surface, and whenever the speed changes, you notice also that the direction will bend a little bit. So based upon the refraction property, Newton predicted that light should be particles. However, Newton's theory cannot be true because when two lights cross path each other, they don't interact as particles. They interact more as a wave. Because if they interact as particles, you would expect them to collide with each other. The two beams, they would collide with each other, and as a result, they will scatter all over. Those involved in the collision, they will bounce off in all directions, and that does not happen with light. What happens actually, they interfere as waves, as water waves interfering with each other. As you see here, the water waves, whenever the waves collide with each other, they create what we call it interference pattern. And that's the case with waves. As you see here, when you drop two pencils in a pond, they basically create what we call it constructive and destructive interference of waves. There was, however, another discovery in the 20th century, which is called the photoelectric effect, which proves that light has the ability to collide with matter and transfer its energy to metal surfaces and knock out electrons. So it has the ability to collide, and hence this is a particle property of light, which we call it photons. So light is not completely a wave, neither particle. Right now we know it has dual property. It behaves as particle in certain conditions and wave in other conditions, and that's what constitutes quantum mechanics. This is an animation of the photoelectric effect. Suppose you have surface of copper, and suppose we shine the light, and notice here the effect of the frequency. Let's say, for example, if we set the light to be in the green region around 540 nanometers, and let's set the intensity here at 30%, nothing will happen here. Now suppose we increase the frequency, and we set it the UV region, nothing is happening so far. Now let's increase the intensity, let's say to 100%. Notice here we are getting electrons out. If we increase the energy more, you can see here we are getting more electrons knocked out of the copper surface. So this proves that light has the ability to collide with electrons, give them energy that enable them to leave the atom and overcome the attraction force with the nucleus. And let's look at some of the questions in homework number 12. Question number 1 here in the homework. You are given the speed of the wave and you are given the distance between two adjacent crests to be 1.5 meters. Now distance between two adjacent crests stands the wavelength. So we are given the speed v and we are given the wavelength lambda. The question is, see, what is the frequency and also the period. Now we know that the speed of any wave is equal to the frequency of that wave times the wavelength. This is the general equation that is applicable on any wave, whether it's sound waves, light waves, water waves, mechanical waves, earthquakes, and so on. Any type of wave will adhere to this equation. To find the frequency, we have to rearrange the equation. So the frequency will be the speed of the wave over the wavelength. The speed of the wave is given to be 2 meters per second. The wavelength is 1.5 meter. Now notice here meter will cancel out and we get the answer in 1 over second. 1 over second is hertz. So the answer will be in hertz. And 2 divided by 1.5 will yield 1.33 hertz. Now regarding to the period, we know the period is the inverse of the frequency. The frequency is the inverse of the period as well, because frequency is the number of waves per second, while the period is the time taken to complete one wave. So they are reciprocal. So now we'll divide 1 by 1.33 hertz, and remember hertz is 1 over second, or wave over second, so the answer will be in second, because when you divide 1 by second, this will give you second. And the inverse of 1.33 is 0.75 seconds. It's basically the inverse of 4/3, which is 3/4. In the second question of the homework, you are asked to compute the wavelength of radio wave, and we should note that radio waves are electromagnetic waves, so they have the speed of light 3 times 10 to the power 8 meters per second, and you are given the frequency of the wave. So if you use the equation, the speed of any wave v is equal to the frequency times the wavelength, we rearrange it to solve for the wavelength. We have to divide the speed of the wave by the frequency. So basically we'll divide 3 times 10 to the power 8. Recall how to use the calculator to express power of 10 notation. So this is 3 times 10 to the power 8 divided by the frequency, and recall that the frequency need to be converted to hertz. So kilohertz here has to be written as hertz, and we know 650 kilohertz is 650,000 hertz. So it's basically 6.5 raised to the power 5, because you have to move decimal point 5 places to convert it from 650,000 to 6.5. And this will yield 461 meters for the wavelength. As you see here, the wavelength is long because it's an AM dial, and AM dial is in meters and kilometers actually. On the second one, it's FM signal, and the frequency is 95.1 megahertz. So now we'll take the speed of light, 3 times 10 to the power 8 meter per second, and divide it by the frequency after we convert the megahertz to hertz. Now recall that mega is million. So 95.1 megahertz means 95.1 million hertz. So this is basically 95,100,000 hertz, which if you write it in the power of 10 notation, it will be 9.5 times 10 to the power 7 hertz, and this will yield 3.1 meter. As you see here, the wavelength is in meter and centimeters in the case of the FM signal. In question number 3, you are given the wavelength of an electromagnetic wave. So you are told that it's electromagnetic wave. So you should realize right away that it has the speed of light. And you are asked to determine the region in the electromagnetic spectrum that it represents. Now if you go back to the spectrum, you can see here the spectrum is given in frequency. So we have to convert the wavelength to frequency. So we'll go back and divide the speed of light by the wavelength. So we'll take the speed of light, 3 times 10 to the power 8 meter per second, and divide it by 6 times 10 to the power negative 6. And this will yield 5 times 10 to the power 13 hertz. So now we'll take this number and go back to our chart here and determine where it falls. Now you can see here 5 times 10 to the power 13 hertz is falling in this region, the infrared region, and hence this wavelength belongs to the IR or the infrared region of the electromagnetic waves. In question number 4, to ask you which one of those frequencies lies in the audible range. Now the audible range is between 25 Hz to 25 kilohertz. That's basically 25 Hz to 25,000 Hz. So the only one that falls within that region, 25 Hz to 25,000 Hz, is B, 2500 Hz. In question number 5, light can travel to Earth from distant star but sound cannot. Why? Electromagnetic waves can go through vacuum, and most of the space is vacuum, while sound cannot go through vacuum. That's why we cannot hear what's going on in space. We can only see it. We can see sun, stars, we can observe supernovas, but we cannot hear them. Question number 6, echo is an example of what? It's an example of reflection of sound waves. When the sound waves hit a wall, it will be reflected back, and that's what constitutes echo. Question number 7, the bending of light when it goes from one medium to another due to the speed change is called what? This is actually the phenomena of refraction. This is why when you look at pencil in water, you'll see the pencil bend or crooked or broken, because the light that is reflected off the pencil will bend when it leaves the water surface and enters your eyes. As you can see in this image, the light that is reflected off the pencil, whenever it leaves the water surface, it will change direction. That's what we call refraction. And whenever it enters your eyes, you'll see the extension of the rays that reach your eyes. So instead of seeing this part of the pencil here in its actual position, you'll see it in an apparent position, which makes it look as if it was broken. And this is also why we see the bottom of a swimming pool closer than its actual position. The speed of light will slow down whenever it enters the water, and it will speed up whenever it leaves the water. And refraction is a very important property of light, and it's actually the property that works behind the idea of lenses and hence telescopes and microscopes. So when the light enters a glass, it will bend. And also whenever it exits the glass, it will bend again because it's moving from one medium that has specific density to another medium that has different density. This causes a change in the speed and hence in the direction of the wave. Therefore, the crafter of lenses can use this phenomena to craft the glass in a way that it will focus the rays on one point and hence give you maximum interference, which will amplify or intensify the waves. Another important phenomenon that is built on refraction is the property of dispersion. Whenever the white light, that is composed of all the visible light, whenever it enters a medium, it will basically bend differently based upon the wavelength. The frequency will remain constant, but the wavelength will change, and hence the speed of the wave will change. And as a result, the bending angle of the wave will depend on the wavelength. So the blue will bend different from the green will bend differently from the yellow, and hence we can get the whole spectrum of light or the rainbow of light by using a prism. And that's what we see in the horizon in a rainy day, where the water droplets will act as a prism because water has different density from the air surrounding it, and hence we can see the rainbow in the horizon due to the water, as you see in this figure, where the light is acting as a prism. The sunlight that enters the water droplets will refract and then reflect it again and then refract, and this refraction angle and the refraction angle will depend on the wavelength. So violet will refract differently from the red end, and hence we can get all the light of the visible spectrum dispersed, and hence we can see the rainbow in the horizon. And going back to the questions again, number 8, so number 7 was about refraction. Number 8 asks about the phenomena that accounts for the fact that waves can bend around corners. And this is actually what we call diffraction, which is different from refraction. Refraction is bending of light whenever it moves from one medium to another, while diffraction is when light bends around corners or whenever it enters a very narrow slit. As you see in this animation, where the light enters a small narrow opening, and as a result it will bend in all directions. So this is the phenomena of diffraction, and its property of all waves. Question number 9, what phenomena account for the changes in the waveform produced by the phase and amplitude relations of two or more waves? This is actually the phenomena of interference. So when two waves overlap, we see a pattern of what we call constructive and destructive interference. Constructive interference are indicated by the bright spots, while destructive interference are indicated by the dark spots that we see here when the two waves interfere. So this is an example of constructive interference where the two waves reinforce each other, hence you get a higher amplitude wave. While this is an example of destructive interference where a crest coincides with a trough, and hence the two waves will cancel each other if they have the same amplitude. And this is why in a microwave you get cold spots and hot spots, right? Well, nowadays all microwaves have a revolving plate, but if you have one of those old microwaves, you will notice that when you heat a tray of marshmallows, for example, some of the marshmallows will melt right away while other marshmallows will stay cold, and this is due to the phenomena of interference. You get cold and dark spots, you get cold spots and hot spots, because in some spots you have constructive interference, while on other spots the waves will interfere out of phase, and hence you get destructive interference, which is a low intensity wave. This will conclude the second part of lesson number 12. I hope you found it educational. Thank you for watching.